Hello everyone, I'm Sri and today I'll be talking about the story of my legendary glider, Bob the Glider. First, let's start with the project description. We were required to design, build, and fly a glider that was less than 16 inches by 16 inches and it had to fly at least 20 feet. It also had to be hand-thrown. The glider could be propelled only by the throw, which meant that there couldn't be a propulsion system built into the glider. The glider also needed to remain intact for the flight to count. The given materials are shown on the bottom right. Now, let's talk about the design process. When I was first designing my glider, I narrowed down the wing designs to either a rectangular wing, a tapered wing, or a swept back wing through research and discussions with my peers. Some advantages of a rectangular wing are that it's easy to construct, and since it has a large area, lift would increase. However, induced drag will increase as well. My second option was a tapered wing. Some advantages of a tapered wing are that there is less induced drag compared to a rectangular wing, while there will still be a large area, which means lift would increase. It is also relatively easy to construct, but through my research, I found that when tapered wings are not constructed properly, the likelihood of the glider stalling increases greatly. Finally, for swept-back wings, they provide longitudinal stability, have high aspect ratios, decrease induced drag, but are very difficult to construct. Now, I also had to make a decision about which tail I wanted to use. My first option was a conventional tail. These are easy to construct, more compact, aerodynamically efficient, but they create more drag and are not popular choices for gliders. My second option was a V-tail. These reduce drag but are difficult to construct, and they may not produce enough stabilization. My third choice was a T-tail. These tails can improve the stability of the glider and can be downsized so drag can be reduced while all being relatively easy to construct. However, they are more likely to stall at higher angles of attack and break upon impact. I also had to choose which adhesive to use. The first option was CA glue. It's very strong but it dries very quickly, which means I couldn't change the position of my glider parts after I applied the glue. It's also very heavy, which means the stability of the glider could be impacted. The second option was hot glue. It's very strong and dries slowly, which means I could make changes to my glider parts after they were glued, in case I misplaced anything, but it's also very heavy. The final option was masking tape. With masking tape, the parts are easily adjustable. For example, if I taped a part of the glider incorrectly, I could simply remove the masking tape and fix my mistakes. However, it isn't very strong, which means that my glider would likely fall apart upon impact. For my initial design, I chose a tapered wing of 16 inches, which was the maximum, so there would be a higher aspect ratio and greater lift. Next, I chose a conventional tail, mainly because it's easy to construct. I found that the fuselage should be around 75% of the wingspan, so I made it 12 inches. The tip cord was 0.75 inches, the root cord was 3 inches, the horizontal tail span was 5 inches, the vertical tail base was 3 inches, and the vertical tail height was 2 inches. The dimensions of the vertical and horizontal tails were chosen based off the fact that the horizontal stabilizers should be around 25% of the area of the wings, and the vertical stabilizer should be around 50% of the area of the horizontal stabilizer. The first design of the glider performed poorly. It was only going around 10 feet and immediately nosediving after. Through some research, I found that this happens when the glider is tail heavy, so I selected a rectangular planform instead to increase lift, moved the wing down, made all the components of my tail smaller while keeping the ratios of the dimensions the same, and increased the weight on the nose of my glider, so that the center of gravity would be around the 25% mark of the length of the fuselage. This worked and went around 30 feet, and I was pretty happy with the results. These are the images of my final glider. I decided on a rectangular wing planform and a conventional tail, and the final design met the 16-inch by 16-inch requirement. A few days later, it was flight test day. Would Bob the glider succumb to the pressure? Well, of course not. Everyone knows Bob the glider performs the best with the pressure at its highest anyways. My glider went 53 feet and 67 feet and made it to the third round of the tournament. In the third round, Bob the glider showed his humility by going only 30 feet and allowing the other gliders to advance to the final round. Now, to measure the center of gravity, I balanced the glider on my finger to find that the center of gravity was 0.6 inches behind the quarter chord line, which also meant that the center of gravity was 3.75 inches from the nose of the glider. To measure the coefficient of lift, I used the formula given and found that it was approximately 0.0322. My work is shown on the slide. Using the coefficient of lift found in the previous slide and the coefficient of drag formula, I was able to find the coefficient of drag to be 0.000137771. My work is shown on this slide. For a summary of this project, we were required to design, build, and fly a glider which could be a maximum of 16 inches by 16 inches that flies at least 20 feet. My personal best flight distance was 67 feet. Looking in hindsight, I wish I'd done more design iterations. I didn't do too many because I was nervous my glider would break down even more during testing and I wouldn't have anything to show during test day. And finally, I've understood the importance of Play-Doh. Without Play-Doh, Bob the glider would have just been a dream. These are some of the sources I used for this report. Thank you all so much for watching my presentation.